Change analysis in remote sensing. So change analysis in remote sensing is one of the 3 apps that that we're learning in this term. And some people refer to these as killer apps. Probably not a great term to use, but it is in common use, and it's it's killer in a good way, right? It kills problems. It solves problems. And so the main purpose for change analysis is to automate really laborious tasks, but there's lots of other things about it that make it really popular and very powerful, because it's used all across the physical and human disciplines. And in particular, it's used a lot now in climate and environmental change analysis that is becoming more and more important in all facets, it seems, of political, social, economic, and cultural life. And it's used widely again in urban change analyses as well, which is particularly relevant for us because we're in such a large and dynamic city. And also it's used to produce these really convincing visualizations. When you see change in change analysis, those of you who have looked at the time-lapse videos, you see this. It's seeing is believing in many ways, and change analysis is a really powerful way of visualizing things that are changing. And change is perhaps the most important thing that we're analyzing now. Various, many different kinds of change, human and physical / natural change. And then ultimately for us as remote sensors, it's also used to produce quantitative analyses of change. And so this is, also very important for us. So I got my first exposure to change analysis in remote sensing as an image interpreter at the Kentucky Geological Survey in Kentucky. And this is an example of a big project that I worked on for a number of years, a subsidence project. We were actually working with people in Illinois and some other states at the same time. So I was collaborating, traveling to Champaign, quite a lot to work with folks in the Illinois State Geological Survey at the University of Illinois in Champaign. And so this is common, not just in Kentucky, but also in, almost every state in the nation, problem of subsidence. So where you have deep mining of any kind, deep mining is something that people do, and things that people do, and particularly when they do them to nature, tend to fail and tend to, have unintended consequences. And one of the main consequences around mining is this problem of subsidence. And so you can see some of the ways that subsidence occurs here. And so when I was working on this, really starting in the 1970s, but in the 1980s in particular, we were working with aerial imagery and aerial photography, and none of this was digitized. It was all analog photography. So I'm talking about stacks, thousands of aerial images covering large parts of the state. Kentucky has 2 coal fields: the eastern coal field, which is everything, in the mountains in the eastern part of the state, and then the western Kentucky coal field, which is more, congruent and very similar to the coal fields in southern Illinois, and it's really part of the same geological region of coal mining. So when you look at this image, this is in Muhlenberg and Hopkins County. It's actually, I think it's right on the county line. And Muhlenberg County, some of you maybe know the song Paradise by John Prine. It was about Muhlenberg County and mining in Muhlenberg County. So when you look at this photograph from 1963, this is a black and white photograph, aerial photograph, and you can see some large kind of kidney-shaped ponds, or these are actually ponds. It's down in this is in the Tradewater River, which is tributary to the Green River, and so you can see these ponds that are occurring. This is in a rural area, a lot of forest, some farmland here, and so that's 1963. Here's 1981. So when you look at this, you can see there's some new ponds and subsidence features that have appeared, and these actually, they tend to look more or less like a mine. You can almost see the pattern of the room and pillar mining that takes place, at relatively shallow depth, 100 feet or sometimes less than 100 feet below the surface. And so, this is a real problem. Here's the geeky guy in his office who was working. And again, you can see here's a stack of photographs, and I'm working through them. So you move one in from this side, you move the other one over, and you have a stereoscope here, and you're looking at a stereo pair. So we're doing three-dimensional image interpretation on a light table. This is why people wear glasses when they get older, from staring into these sorts of things for 8 hours a day for months and years at a time. And so this is how I was doing this. And so this is actually in the Eastern Kentucky coal field. This is some more of this work. So this is in Ashland, Kentucky. Ashland, Kentucky is probably most famous for being I think the birthplace of, and certainly the early childhood home of Miley Cyrus. She actually came from Ashland, Kentucky, and her father, Billy Ray Cyrus, from Ashland. Also, the Judds are from Ashland. Ashley Judd and her sibling and mom, who are famous country stars. So Ashland, has some kind of different problems. When you're looking at it, you can see it's a lot rougher. This is in the eastern coal field. Here's some areas where mining has taken place. So we're actually looking and we're identifying places where mining has taken place. A different kind of mining here in eastern Kentucky, more Appalachian style coal mining of various types. And this is right in the city. And so you have some problems with this. And then so you can see I'm marking up the photograph. Again, still just working with something that is an analog, with nothing digital at this point. And then, transferring this photogrammetrically to a published map, to a topographic map, and then the topographic map eventually is used as the base for a published map. So this kind of work takes months to do, right? It's very laborious, thousands of photographs, lots of staring into fluorescent light tables, and so you wind up with a published map here that is, ultimately these maps actually got digitized. So they were digitized by someone and actually went into the state geographic information system. So fortunately now for us, we have powerful GIS. We have very precise georeferencing, and particularly georeferencing of our satellite images that we're working with. So here's an example, and again, this is what georeferencing gets you. We didn't really have that kind of georeferencing, and we had to solve all of those problems more or less through the work process that we worked through over a period of months, as I was saying. So it was a very laborious and tedious task to produce a published map like this thing here. So here's a Landsat scene from 1985 of the O'Hare Airport region, and you can see this is a Landsat 5. Here's the date, 1985. It's the 298th day of the year, so it's probably in the fall. And we're looking at channel 3, so we're looking at visible red. And so there's the O'Hare Airport in 1985. Here it is in 1987. Here it is in 1995. And here it is in 2003. And then here it is in 2010. So you can see the change that's taking place through these 5 images or so, you can see different changes to O'Hare, new runways down here, Carpentersville, subdivisions being cleared out, hundreds of homes being demolished, and the expansion of the airport on the southern end of the airport and the northern end of the airport as well, and other expansion. There's actually the international terminal that gets built at some point here. Let's see, it's 1987. So here I think you can see the international terminal being built in the 1990s. So you can see there's some big changes taking place out here. And so how do we analyze this? Well, because of the tight georeferencing that we have, that's really at a sub-pixel precision, so that when you look at these different images, you have the exact same pixel sitting on top of the next pixel and the next pixel, as our georeferencing has improved through the years, our georeferencing of these raster data. So that's really where a lot of the power that we have in change analysis comes from. It's through the marriage of remote sensing to GIS and the combination of these two technologies into a big master technology, which now is called GIS and remote sensing. But remote sensing really can't work in the way that we want it to work without having that powerful GIS behind it, where we have powerful georeferencing and also the attribute data that comes with the GIS data models of various kinds. So with the attribute data that we have in raster data is the reflectance data, right? So here's a problem, and this is one of the problems that we have to solve when we're doing change analysis, and we can begin to solve this problem. One of the problems that we have is the effect of changing sun elevation from one time of the year to another time of the year. When you look at winter scenes that are at 10:10 in the morning, local sun time, so it comes back at exactly the same time from one scene to another scene. The difference between summer and winter in Chicago is extraordinary. It's on the order of around 40 degrees or so between summer and winter at 10:10 in the morning when the satellite comes back. Every time it comes back, it's always just about the same sun time, right? Around 10:10, roughly. With a bit of change, 5 minutes or so in either direction. So this is a problem. Now, why is it a problem? Well, it's because as the sun elevation changes, the reflectance in the hemisphere around a pixel, as the sun strikes the pixel and illuminates the pixel, the reflectance that takes place around that pixel is it's very variable. I mean, it shifts around. It actually shifts around during the day too. But because we're coming in at the same sun time, we've solved that part of the problem. The other problem we have is this change in sun elevation that's seasonal. The sun is, in summertime, it's up in the 60 degree above the horizon range, whereas in the wintertime it's down around 20 degrees or so. And I don't mean temperature, I mean the angle of the sun above the horizon here in Chicago. So it's very, very, very great, the sun elevation. So this is a problem that we have to solve. And just to give you an example of how much this changes, just through a day, this is an image that shows us a field instrument. We don't have one of these at DePaul, but they're quite big and they're quite expensive. This is called a goniometer, a field goniometer, and what it does is it takes a three-dimensional scan of the reflectance of an area inside of a circle, which this would be centered on a pixel if we were doing this as a field operation in support of remote sensing. And when you plot the reflectance, and this is in, you can see it's in visible red, band 624, that's 624 nanometers, with probably a very narrow band because this is a field spectrometer here, so these are very narrow band spectrometers, 10 to 20 nanometers wide, so it's a real narrow sliver of the spectrum. And you can see here's 8 a.m. of this location. Here's what the reflectance surface looks like. So you can see the sun's coming in from the east, and it's being reflected out to the west. So this is how you always have this specular component in the reflectance of a given pixel. So here's 8 a.m., here's 9 a.m. You can see it shifting to the southeast. Here's noon. So you can see it's close to straight overhead. This is actually down in South Carolina. And so there's still a bit of spectral reflectance here. And then here it is at 4 p.m. So now you have, again, this spike here. That's the spectral spike in this curve of the reflectance. Again, in this part of the spectrum, in this particular location. So again, this is just to illustrate how variable the reflectance is with changes in sun elevation. Now these changes are the daily changes, the diurnal changes in sun elevation, but in fact, the change that we're going to be concerned with is trying to solve is the seasonal change in sun elevation. So it's always going to be more or less from the same azimuth, from the same direction, because it's going to be close to the same sun time, but it will be different in elevation. So you're going to see more of a difference, like a change from this to something more like this at our latitude, right? So in radiometric correction, again, you have to do it anytime you have a pretty significant, and you really, it's less of a worry if you have the same date, certainly, or where you have very similar, very close sun elevations, or a significant difference in the date of our imagery. And this is more than a week or two. You need to do this kind of radiometric correction. So in doing so, we make this correction by taking the pixel values in all of the images you're working with. So if you're working with two images, you have to do it to both images using their own sun elevation and taking the sine, which is the opposite over the hypotenuse. We all remember that from our high school trigonometry. And you use the raster calculator, typically in ArcGIS, and you divide the pixel values in all the images you're using by the sine of the sun elevation. So I know this sounds kind of crazy, but what this does is and let me give you here, I'll give you a little hand illustration here. If you have two imagine these are the histograms of your two images. It brings them closer into concordance. So that's what happens when you have a change in sun elevation. They tend to shift. The histograms tend to shift, to be less bright in the winter and more bright in the summer. And it tends to shift both of these to align them more closely so that when we do our change analysis, our automated change analysis, we've accounted for that change in sun elevation. Okay? So, all right. Now, so the approach that we use is something called temporal image differencing. And so in temporal image differencing, you use two dates of imagery. Okay, so you have two dates of imagery, and you're interested in the change that took place between these two dates. And you do radiometric correction first. You do all this, you apply all that to the images you're using, if you need to do that, if there's a significant difference in the dates. And then we take the older image, typically, just to be consistent, and we subtract the older image from the newer image. So when we do that, assuming that we've done a good correction, good radiometric correction, where there's no change, the value is going to be fairly close to 0. Now it may be shifted a bit off of 0, but the value, the value where there's no change is going to be fairly close to 0. Now where there is change, the value is either going to be positive or negative. If it got brighter in the newer image, then the values on the positive side of our histogram are going to be places where the pixels got significantly brighter. If it's on the negative side of our histogram, it's going to be places where the pixels got significantly darker. Now, what we do after that is we classify the image. So actually you go back in and you take some of the skills that you learned in density slicing and we apply those to our histogram. And most often we're interested in both tails of the histogram. But sometimes we may be interested in only one or only the other if we're looking at a specific type of change. And this is sometimes completed in the image analysis window in ArcGIS 10 and the subsequent new versions of that. We're working on 10.6 right now. So here's a typical image differencing. So again, and you have to remember, these are always done on the same channel. So you have one date and you're working with a particular channel, one channel, and on that date and on your other image, your older image, in this case, image 2. So you have image 1, the newer image, image 2, the older image, and these are both in the same channel. So there's really no fixed, hard and fast rule on what channels we use, but a general rule of thumb is that for cultural change, we would probably use visual channels for changes that are human, in most cases, but not always. And you'll see what I mean as we go along and as you start to do this, right? So deforestation, for instance, would we use a channel in the visual or a channel in the infrared? Think about that one, okay? But we always, when we're doing image differencing, we use the same channel in both of our images. So this is the simplest case where you're looking at the change between two images. And so here you can see we take this image, we subtract this image from it, and we get a difference image, okay? And this is the difference, in a mathematical sense, between these two images. So you can see here are 3 pixels where you have negative values in the difference image. You have some 0 values, and then you have a positive value. And again, these are all integers. These are 8-bit integers. So the zeros are what? The zeros are no change, right? So this is where no change has taken place. In these pixels, the pixels have gotten significantly darker. In this pixel, the pixel has gotten significantly lighter. So you can see these are red, and this one that's supposed to be green, but it's kind of grayish green, you might say. So this is the simplest case. Here's another possible case, okay? Here's where you have 3 images. We were looking at O'Hare Airport earlier where we had 5 or 6 images, and you can see here's image A, image B, and image C. Again, all corrected and all the same channel. It could be a visual channel, it could be an infrared channel. But in this instance, you get 2 change analyses because you have 2 periods between images. All of these corrected with their own sun elevation, and then differences, 2 separate difference images produced from these changes. Now, why would you do something like this? Well, one of the reasons would be what if we're interested in analyzing whether change is slowing down or whether change is speeding up? And so if we have two different change images, then we can quantify the amount of change. We can calculate using some tools that we have, some GIS tools. We can calculate the area of change, of a particular kind of change that's taken place wherever we're looking, and we can compare that on a daily rate of change basis, because you have to, these intervals between these images, you have to reduce these to a number of days so that you can calculate a change per day. So we use the day as our temporal unit. And this is because, you know, these may be different dates, they may be different. So you really need the precise number of days between these dates, which is not difficult to calculate. This is really on the level of arithmetic when we start thinking about it, right? Okay, so this is, again, this is where things start to get more complicated, but also more powerful, because we can produce results now that are more useful, where we can start talking about rates of change. We can make claims, right? Claims to truth about the area that we're studying. This is sort of the highest level, in my eyes, of change analysis, certainly, but also more generally in science. This is what we try to do in science, is we try to produce claims to truth. Okay, that's what we're after. We're after truth in science. Okay, is it, you know, is truth objective? Well, that's a discussion for a different time, right? So here we go. And this just gives you an example of a simple change analysis. Here's 2003, 236th day of the year, channel 3, and here's 2010, the 255th day of the year. I probably would do a radiometric correction on these. And here's our change analysis. Here's our difference image classified. Okay, so now we've classified that difference image. Now, how did we do that? And so in this instance, the green areas are areas that got brighter. See them? And the red areas are areas that got darker. See them? Okay. Now, how did we do that? Well, here's our histogram. And this is a histogram of a difference image. And difference images very often, almost always actually, look almost normal. They almost look like asymmetrical, not asymmetrical, but asymmetrical, two different words there, asymmetrical curve, almost like a normal curve. But you can see the mean here is -9, so it's kind of close to 0 in this range. You can see it ranges from 187 out, or -187 out to +194. Okay, so it's actually they're probably using more than 8 bits to store these numbers. Okay, these new numbers, because these are real values here with decimal points on them. And so in any case, because these, and especially once we've corrected them, they're going to be real numbers. So here's our histogram. So now the skills you learned in density slicing become useful as you start nipping at those tails of those histograms. So change analysis, right? Very powerful tool. And again, I'm going to show you just a little bit of an activity 4 that I'm working on, because I always work on these. As you're working on them. Here's my activity 4. So you can see here I have channel 3 and channel 3. So this is channel 3 in 2001. Here's channel 3 in 2010. this one's Landsat 7 and this one's Landsat 5. The Methuselah, Landsat 5, lasted for so long. And so you can see here, I've got, let's take a look at them without the change. So here, this is actually the Glen in the northern suburbs that was redeveloped during this period of time, largely. Actually started in the 90s. But here's the raw difference image, ranging from negative 255 to positive 255. And here's our difference image. And then what I did is I clipped it. Okay, so this is a clip of that same image. Okay, and then I did a reclassification. Okay, where so you can here you can see I should have different colors on these, but this is a reclassification. And in our reclassification, I took this value range and I assigned a 1 to it, and I took this value range and I assigned a 2, and I took this value range and I assigned a 3 to it, just to simplify things for us as we're doing our change analysis. Okay, so change analysis. This is a powerful, very powerful technique, and we're going to be starting our activity 4s, and this is what we're doing in our activity 4. Okay, so change analysis. All right, cool.